Imagine this. You're a superhero about to give that big, inspiring speech right before the final battle, the one that rallies the troops.
Yeah.
The words are all there in your head, perfect, ready to go. But then, nothing. It's like the launch sequence just seizes up.
That is such a good analogy. It's like trying to start a car and the engine just sputters. For
Hmm.
most of us, talking is, well, it's automatic. We don't even think about it.
Right.
But for millions of people, that whole motor mechanism stutters. And historically, it was just written off as, you know, nerves or a psychological problem.
Welcome to the deep dive. Today, we're unpacking a huge survey of the research, epidemiology, genetics, neurobiology to really get to the bottom of this. We're moving past all those old ideas.
And our mission today is to show you that stuttering is actually one of the most complex neurodevelopmental disorders we know of.
We're going to follow the breadcrumbs from the cellular level all the way up to the brain circuits to see what's actually misfiring in the engine room. So let's set the stage a little. This is more common than people think. Around, 5 to 7% of kids will stutter at some point?
That's right. And thankfully, most of them, about 75%, recover on their own. But for about 1% of the population, it does persist into adulthood.
And those numbers really tell a story, don't they? It's not random. It's deeply connected to how the brain develops right at the beginning.
It's baked right into the speech acquisition process itself.
Okay, so let's dive in there. Who stutters and when? What is this critical window we keep hearing about?
So developmental stuttering almost always pops up during that super intense period when kids are learning language. We're talking peak onset between ages 3 and 6.
And what's really fascinating to me is the sex skew.
Oh, it's huge.
Ugh.
At the very beginning, when kids first start stuttering, the rates for boys and girls are pretty much 1-to-1, almost equal.
But that doesn't last.
Not at all. You fast forward to adulthood, you look at who has persistent stuttering, and suddenly males are affected 3 to 4 times more often than females.
Wow, so there's some kind of protective factor happening for girls.
It seems that way. The female brain appears to be more resilient or just better at repairing whatever that underlying neurological glitch is. It's a huge area of research.
That's a massive insight. And for anyone listening, parents, educators, here's the big headline. Spontaneous recovery is the norm.
It is. 75 to 80% of kids who start stuttering will stop on their own by late childhood. Recovery is the main story.
So if recovery is the default setting, then the really critical question becomes, how do we spot the 20% who won't recover on their own?
Exactly. And the research points to 4 major red flags, 4 things to watch for that help predict who might need intervention.
Okay, let's break these down, because this is probably the most actionable part of this whole deep dive. What's the first risk factor?
First is the age of onset. And this one is a bit counterintuitive. You'd think earlier is worse, but it's the opposite. Yeah. A later start, so after age 4, is actually a bigger risk factor for it persisting. Kids who start before age 3.5 have a much, much higher chance of recovering.
So the earlier the brain starts to wrestle with the problem, the better its chances of fixing it.
That seems to be the case.
Okay, so later onset is a red flag. What are the other 3?
Second, a positive family history.
Yeah.
If you have a parent or sibling who stutters, the chances of it persisting go way up, which of course points straight to genetics.
Right.
Third is just time. If a child has been stuttering for more than a year, the pattern is probably becoming more entrenched in their brain. And fourth, any co-occurring speech or language issues.
Like trouble with articulation or something.
Exactly. If there are other challenges, it suggests a more widespread vulnerability in the language system, making recovery less likely on its own.
And that brings us right to the source code of the problem, the genetics. The evidence here is just, it's overwhelming.
It really is.
Yeah.
Twin studies have heritability estimates as high as 0.84.
So in plain English, that means what? Up to 84% of the risk is just written in your DNA.
That's right. It makes it one of the most heritable conditions we know of in speech pathology. It's not about parenting. It's not stress. It's biological.
And this is where, for me, the research delivered a real wow moment. Because you'd expect to find genes related to, I don't know, muscle control or hearing.
Right. Something directly tied to speech.
But that's not what they found. The discovery points somewhere completely unexpected.
It points to lysosomal enzyme trafficking.
What you mean, the cell's garbage disposal system, the part that breaks down waste.
The very same. The main genes they've identified, GNPTT and GNPTG, are basically responsible for putting the right shipping label on materials headed for the lysosome, the cell's recycling center.
So if that labeling system is broken,
Then crucial proteins and other materials don't get where they need to go inside the neurons. The whole maintenance system is faulty.
okay, so connect the dots for us. How does a problem with cellular housekeeping lead to a stutter? That feels like a huge leap.
Well, think about it. Speech is one of the most complex and rapid motor skills we have. If the neurons responsible for that can't clean up and recycle their components efficiently.
They can't fire as quickly or in the right sequence. The whole system gets laggy.
Exactly. The failure is systemic. It's affecting the very scaffolding needed for that rapid-fire communication. It's like finding out the Millennium Falcon's hyperdrive is failing because of a problem in the garbage compactor.
That's a perfect analogy.
Now,
And there's a specific mutation they've pinpointed, right?
there is the GMPTT p-gluconi 1200 ELISE variant. And what's important is that this specific variant shows up way more often in people who stutter than in the general population. It's a direct molecular link.
Incredible. So we have a genetic blueprint that makes the brain's cellular maintenance a little shaky. Now let's zoom out to the brain itself. How does that weakness cause the engine of speech to stall?
So the modern view is that stuttering is a disorder of speech motor program initiation. And the part of the brain responsible for that is a circuit called the cortico-basal ganglia thalamocortical loop. Let's just call it the cortico-BG loop.
Cortico-BG loop. And that's our timing mechanism.
That's the clutch in the transmission, going back to your car analogy. The basal ganglia, specifically, is what says go for each syllable. It initiates the motor program for V, then smoothly shifts to initiate the program for cat.
And if that clutch is faulty, the whole thing gets jerky and stalls.
Precisely. The signal gets disrupted. And we can actually see this now with brain imaging, starting with the white matter.
A white matter. That's the wiring, right? The brain's fiber optic cables.
That's right. And studies using DTI imaging consistently find reduced integrity, what they call fractional anisotropy, or FA, in the white matter on the left side of the brain.
Lower FA means the cables are frayed, essentially.
Yes, especially in a big bundle of cables called the superior longitudinal fasciculus, or SLF, which connects the key language and motor areas. The wiring is compromised.
And here's the kicker. This ties directly back to what you said about recovery.
It gives us physical proof. In kids who spontaneously recover, we can literally watch those white matter metrics normalize over time. The brain is repairing its own cables.
Wow.
But in kids where it persists, those deficits often get worse. The problem becomes more and more hardwired.
So recovery isn't just behavioral, it's a measurable physical rewiring of the brain. That's powerful. So what about the gray matter, the processing hubs?
We see changes there too. Reduced gray matter volume, so less processing power in key left hemisphere motor areas, the inferior frontal gyrus, premotor cortex, the putamen.
But I remember reading something about the brain trying to compensate.
It does. This is fascinating. While the left side shows less gray matter, we often see more gray matter in corresponding areas on the right side, like the right Rolandic operculum.
The brain is firing up the backup generator.
It's firing up the backup generator. The right hemisphere is trying to take over a job that the left hemisphere is specialized for.
But it's not a perfect solution, clearly, or the person wouldn't stutter.
It's not. The right hemisphere just isn't as efficient at the super fast, precise timing required for speech. It's a workaround, not a fix. And it introduces its own noise into the system.
So functionally, when you put someone who stutters in an fMRI and ask them to talk, what do you see?
You see that exact pattern played out. There's hyperactivation overdrive in the right motor cortex. The backup system is working way too hard.
And at the same time?
At the same time, there's hypoactivation. It's underworking in the key areas we talked about, the basal ganglia, that clutch mechanism, and also in the auditory cortex.
Which brings us to the final piece of this puzzle, the neurochemistry, the fuel for the engine.
Yes. We've got a faulty clutch and frayed wiring. Now let's talk about dopamine.
Right. Dopamine. Usually we think of it with reward or movement in general. How does it fit in here?
The basal ganglia is just swimming in dopamine receptors. It's incredibly sensitive to it. And what PD scans show is an elevated level of dopamine synthesis in people who stutter. It's a hyperdopaminergic state.
Too much dopamine. So the gas pedal is stuck to the floor.
That's a great way to put it. That excess dopamine is thought to actually inhibit the metabolism in that circuit, jamming up the timing mechanism. And the proof is in the medicine.
What do you mean?
Well, drugs that block dopamine receptors, like haloperidol, have been shown in trials to actually reduce the severity of stuttering.
That's a direct chemical link. It's so neat. It ties everything together.
It really does. Because think about it. The peak of stuttering onset, ages 3 to 4, is also the exact time in development when dopamine receptor density in this part of the brain is at its absolute maximum.
And the brain is also doing all that synaptic pruning, trying to become more efficient.
Exactly. So you've got this perfect storm. You have a genetic vulnerability in the wiring, and you flood it with the highest ever levels of this starter chemical, all while the brain is trying to learn its most complex motor skill. That's when the system overloads.
Okay, so knowing all of this complex science, where do we stand with treatment? What actually works?
The biggest success, by far, comes from getting in early. For preschoolers, the gold standard is a method called the Lidcombe Program.
And it's really effective.
Incredibly. It shows about a 77% reduction in stuttering. Compare that to the 43% who recover naturally. The difference is huge.
What makes it work so well?
Its main strength is that it's parent-led. It gives parents tools for providing gentle, positive feedback for fluent speech, right in that critical window of brain plasticity. It helps the brain find the right path before the wrong one gets paved over.
What about for older kids and adults, where the patterns are more set in stone?
It's tougher, but there's still progress. For school-age kids, speech restructuring programs could get about a 50 to 57% reduction. For adults, it's often a combined approach.
Meaning
You combine the speech techniques with something like cognitive behavioral therapy or CBT.
to deal with the anxiety and avoidance that builds up over years of stuttering.
Precisely. You have to treat the whole person, not just the speech.
And what's on the horizon? Any new tech?
Yes, actually. Non-invasive brain stimulation, like TDCS, is showing a lot of promise. On its own, the effects are modest, but when you combine it with speech therapy, the results get substantially better. It's like it primes the brain to learn more effectively.
This research survey has answered so much, but what are the big lingering questions that scientists are still trying to solve?
The biggest one is still causality. It's the classic chicken and egg problem.
Yeah.
Do these brain differences, the frayed white matter, the reduced gray matter, do they cause the stuttering?
Or are they the result of it? The brain changing because of years of struggling to speak?
Exactly. And we still need to map the full pathway from the GNPTD gene to the circuit failure. How does a garbage disposal gene break the timing of speech?
And the big one, the sex difference. We still don't really know why girls are so much more likely to recover.
Unlocking that could be the key to developing much better, more targeted therapies for everyone.
Okay, so let's distill this all down. What are the key takeaways from this deep dive that you, the listener, should walk away with?
I think there are three really big ones.
Go for it.
First, and this is the most important, stuttering is a neurodevelopmental disorder. It has a strong genetic basis. It is not a psychological problem or a sign of weakness.
Okay. Number two?
Number two, the core issue is in that cortico-BG loop. It's a problem with initiating and timing speech motor commands. It's an engine failure, not a fear of driving.
I love that. And number three?
Third, recovery is a real, measurable neurological process we can see in the brain. This means that early intervention during that critical plastic period is the single most important thing we can do.
The big picture seems to be a move toward precision medicine, using genetics and brain imaging to tailor a therapy for a specific person's brain.
Getting rid of the one-size-fits-all approach, that's the future.
Which leaves us, and you, with one final, pretty heavy question to think about. If we get to a point where we can use these genetic and brain markers to predict, with real accuracy, which kids won't recover on their own, how early do we intervene? And what are the ethical responsibilities that come with knowing a child's likely neurological future, maybe even before they've said their first full sentence?
It's a question that puts a lot of power and a lot of responsibility in the hands of science.
It really does. Thank you for joining us in the Deep Dive Lab for this exploration of the brain's speech engine. We hope you learned something new.
And if you enjoyed this journey into the research, make sure you subscribe so you can catch our next deep dive.